welcome. Let us start lecture 16. Today we try to the topic is again of course the explanation of corrosion events on the basis of mixed potential theory, and we have already discussed the situation where two active metals are galvanically coupled in an electrolyte when both the metals are active separately in that electrolyte. And we have seen that in case of zinc and iron, the zinc dissolution increases and the iron dissolution decreases. That means the iron gets protected at the expense of zinc. And we have also seen that iron, the cathodic reaction, which is hydrogen evolution reaction in the case what we have considered, that preferentially takes place on iron surface, and on the zinc surface the hydrogen evolution reaction decreases. So, that suggests that iron is acting as a cathodic surface, because since we have already understood that on the surface where cathodic reaction takes place, that particular surface we call it cathode, and anodic reaction preferentially takes place on a surface which is considered as anode. So, in case of zinc and iron, we have iron as cathode and zinc as is anode, and iron is protected. So, that particular, and actually the situation what we consider here, the theory of sacrificial anode for the protection of steel object. So, this steel object could be pipeline or rebar or ship hull. So, all those things are possible, but sacrificial anode is nothing but, as we have mentioned, that cathodic protection we do it by using sacrificial anode. The cathodic protection, if we consider, we have two segments in that cathodic protection. One is of course sacrificial anode, another one is impressed current cathodic protection, which is call it as ICCP. Now, the sacrificial anode, the mixed potential theory, we have explained in lecture 15 with the reference of hydrogen evolution reaction as the cathodic reaction, but it can also be possible in atmosphere, and this comes into picture. This particular sacrificial anode effect will come when will appear when the zinc coating over the iron surface is damaged at local positions. For example, if we have an iron surface, this is iron surface, and then this is my zinc layer. So, this is iron, this is zinc, and when zinc is not damaged, the corrosion behavior is basically nothing but the corrosion of zinc. But there could be a situation where local position could be damaged. This is the segment which is damaged, let us say. So, that time iron is exposed. So, this particular part is exposed. Now, in case of environment, the reduction reaction is this. This is the reduction reaction, a normal atmosphere, and of course, this is zinc, this is iron, and the anodic reactions, this is reduction reaction or cathodic reaction, I would say, and this becomes and zinc. So, these are the two anodic reaction. However, the theory of galvanic coupling between two active metals we have explained in lecture 15. If we try to draw it again quickly, and this time we will not put all those marking, you can go back and see how the situation, how the things were drawn. So, this was the situation. So, we are just this is E equilibrium cathodic reaction, and this is E equilibrium anode 1, this is E equilibrium anode 2, this is A1 and A2 are basically anode 2 anode materials. Okay. And in this case, let us say put it like this, E equilibrium of iron, and this is E equilibrium of zinc. And why we have added it? We have to add it because we have to maintain that mixed potential theory. So, this line indicates IA total is nothing but IA of iron plus IA of zinc, and this line IC total equal to IC of cathodic reaction. Here it is oxygen, I can mention it to be oxygen reduction on iron surface, and this is IC oxygen reduction on zinc surface, and this point is nothing but E mix. Now, when we have this particular situation, so I can draw a line corresponding to the E mix. I could see that this point belongs to A of iron, and this is the point belonging to IA zinc, and of course, if we try to see the other current densities, this particular is this is the connection between the horizontal line drawn, this is log I axis, this is E axis, horizontal line drawn across the point of E mix with reference to log I axis. So, this is IC oxygen evolution reaction on iron, and this becomes my this is the connection which is IC oxygen over zinc surface. Now, I could see that this is greater than this, however, this is here also I could see that this is greater than this. So, that means over iron I am having preferential, this iron, this preferential oxygen reduction, So, it becomes cathode and zinc preferential dissolution which becomes anode. So, now interestingly in case of atmosphere, when we have this kind of thing, so this becomes cathode. So, that means the cathodic reaction, which is nothing but this, happens here. So, it takes the shape of positive electrode, and then this region are anodes where dissolution takes place. So, that means so this becomes negative electrode, negative. So, the current will flow in the electrolyte from negative to positive. This is the current flow, and in the conductor, which is nothing but the metal, the current flows from this to this. And another interesting part what we could see, that if we consider only the iron part, this is the iron part, this two lines, let me draw it with this, these two lines basically the iron part, and this was the dissolution rate when iron is exposed to environment. Now, after we have connected it to zinc, the dissolution rate of iron has moved from this point to this point to this point. Now, when we move it, one thing we could see, interesting observation is, I could see that if we consider this is to be my corrosion potential individually for the iron, if I can take the potential downwards and bring it to this level, okay, I could see that the iron dissolution rate can be decreased. Now, when we do this, that means individually if we consider only the iron part according to that particular drawing, if we see the iron part, so this is E equilibrium oxygen, this is E equilibrium of iron, and if we extend this particular line like this, now these are the 2 points. So, it was the corrosion potential E core, and these are the corresponding I zeros, and this is the I core of iron, and this is in log scale and this is in potential. Now, as per this drawing, I could see that when iron is exposed individually, the potential, if the potential can be taken downwards with reference to the E core for iron, I will experience lower corrosion rate or the dissolution rate of iron, because the dissolution rate will move from this point to this point because of potential drop. So, here also if I can have a potential drop like this, then this line, this is the cathodic line, this IC line will keep continue along in continue in its path, and then we will come to this particular region. I could see that IC of oxygen and IA of iron, these two positions are changing. So, the corrosion rate goes back from I core to IA nu, this is much lower in the log scale. So, the corrosion rate of iron reduces, but the cathodic reaction rate on that iron surface increases. This is the typical concept of cathodic protection. Where the intention is to increase, one is increase IC. So, it reduces IA, and when we do that, potential drops from E core. So, these two concepts, that increase of IC and reduction of IA and potential drop from the steady state potential, which is nothing but E core in this particular situation, that is the basic principle of cathodic protection. Now, here also we are getting actually cathodic protection, because of this zinc coupling, the potential has been taken downwards from the E core of iron. So, this is my E core of iron when iron is individually exposed. And when you do that, if I try to see the circuit, this is iron and this is zinc, and they are in an electrolyte and they are connected. So, what we have done? The potential has been taken downwards. So, the zinc is acting negative, this is positive, and I could see that the IC, so that means electron will be generated more here. So, this electron will move this way, this is electron movement, and comes here on the iron surface. So, electron increase means IC increases, and on this surface we have cathodic reaction, because of the consumption of this electron. So, O2 plus 2H2O plus 4E equal to 4OH minus, since in environment atmosphere we can consider it to be near neutral situation. So, actually I am increasing the IC. Now, here in this particular situation I am increasing IC, but whether, let me see whether here also IC is increasing or not. Actually IC is increasing, because I could see this situation is prevailing. So, on the iron surface IC is increasing. So, this IC line is following this track. So, IC has increased. So, the same principle is holding true here. So, the galvanic protection of iron by zinc is nothing but an example of cathodic protection. And here we are actually consuming zinc, because in this particular situation zinc corrosion rate has increased after coupling. So, this is a mode of sacrificial anode. Now, this principle can be true, can be done separately or differently. For example, if I have a situation, this is an electrolyte, let us say. Now, where we have iron object and this is iron object which is to be protected. I can, instead of having zinc which dissolves, and because of the dissolution we have extra electron, that electron comes to iron, and actually we are increasing IC of that particular reduction process. Okay. So, I can also have an anode, this is anode and this is cathode. So, whenever we try to protect any component by this cathodic protection, that particular component is to be made anode, cathode. So, we have an anode, and in this case this becomes cathode and this becomes anode. So, here also we are making the same situation, but here if we do not want to dissolve anode, so this does not dissolve. So, how could we have this particular principle to be met? Now, we can use an external power source, which is a DC source. So, I can connect it to a positive terminal of a battery and a negative terminal to iron. So, that times the I, which is the current, flows this way, and then current will flow like this, current will go, this is an electrolyte, and here it is, I have said that these are these two things are is basically exposed to electrolyte. So, the current is flowing and then it is going back. This is the current, the system current, the electrical current. Now, since this is connected to the negative terminal, the electron will flow this way. So, when electrons are flowing this way, so this excess electrons need to be neutralized, because the charge conservation had to be made. So, this electron will be neutralized by having this reaction. So, now this is also a cathodic reaction. So, wherever cathodic reaction takes place, we consider it to be cathode. So, here this is cathode, this iron becomes cathode, and the anode which does not dissolve, there we have anodic reactions. Okay. But if it does not, but since it is not dissolving, so we cannot have generation of electron because of the dissolution what we had in case of zinc dissolution, while we connected zinc with an iron object. But these anodes are called auxiliary anodes. So, this is auxiliary anode. So, this does not dissolve, but it actually acts as an anode in that particular system, so that it can be connected to an external battery. This particular mode of cathodic, here also we could see that the iron which is to be protected is made into cathode. So, this is also cathodic protection. But here we are supplying that negative current to the iron, that means this negative current to the iron piece or iron object from an external power source, a DC power source, by having that circuit completed with an auxiliary anode. So, this is called impressed current cathodic protection, or ICCP. So, let us stop here. We will continue our discussion on this cathodic protection and try to see the effect of different other metals which are acting as a sacrificial anode on the effect of on that potential drop and reduction in corrosion rate of that of iron piece. Let us stop here. Thank you very much.